So the short version is a Merkle tree is a tree structure, and there's so many different cool variants of tree structures, right? B trees, which we've talked about a lot, Merkle trees, there's binary search trees, there's prefix trees, there's AVL trees, there's so many. But this is one specifically for studying and tracking changes either in projects with lots of files or changes in large files. And the way they work is pretty cool. The example that I'm showing here is based on like one specific source code project. It's along the lines of how things like Git work, right? Because if you have a Git repo, it needs a way to be able to track, which files have changed, which files haven't changed. And the way it uses Merkle trees is a little more sophisticated. There's also applications like Cursor, right, which is a code editor that is tracking changes and indexing and sort of vectorizing your code base. And again, I don't know all the implementation details, but it also uses this to help track what code is changing and synchronizing that with remote servers. So the basic idea here is I'll zoom in just to this part. So say you have a project like we see here. This is a very small one, but I have a source directory with a couple of TypeScript files in here. I have a test directory. Of course, typically your project for a large code base might have tens or hundreds or even thousands of individual files, but here we have a small one, so we can build a simple tree for it. And what we're doing here is we want a way to have a local copy of all this code, like a Git repository, and also have a copy of all these things on the server. But what I don't want to have to do is every time I make one code change in one file, I don't want to have to recopy this entire directory to the server, because that'd be a very inefficient use of bandwidth. It would make just things slower, right? It would make the servers have to do more work and more I/O. So I want a way to very efficiently be able to detect synchronization differences between the server. And if I know, hey, only app.ts changed right here, let's just resync app.ts with the server as long as I can validate and know confidently nothing else has changed, right? So what you can do is in some piece of software that's running both on your client, your local machine, and on your server, you can build these Merkle trees. And let's zoom out and scroll over to the tree itself. What we've done is we've taken that simple directory and we've built this entire tree structure out of it. So as you can see, every one of those files, which was just a regular TypeScript file, we're considering those are leaf nodes in this case. And what we do is we generate a hash for the contents of every one of those files. And these are actually the first 7 characters of real, I think it was MD5 hashes that I took, but some kind of hash that I took of all these files. And so we store that in these nodes. And again, this could be structured differently. You could take one big file and divide it up into many chunks, and each of those chunks is one of your leaf nodes, and you take a hash of a file that's chunked. So this isn't only applicable to like a project that has 100 files. It can also be used to sync one single large file or several files that are chunked up in different ways. So we compute those hashes, and then the parent of each one of these, like this right here, or we'll use app here. So this hash, ff64b4b, what that is the concatenation, the hash of the concatenation of 02D9C81 and 9AA628F. So I concatenate those two strings together and I compute a new hash, and that's the hash for this parent, which is like the node for a directory. Same goes for API, same goes for test. Source, this is a hash of the concatenation of this individual file's hash plus the hash of this inner node plus the hash of this inner node, concatenate those together, compute a new hash and do this. And finally, the root hash is a concatenation of these. So what this means is, as long as you are maintaining this tree, like you're writing local changes in the code, every time you make a code change, let's say I change scraper.ts, right? So I make a code change here, and this would propagate a change up to here. Maybe I'll change this color to red to indicate that. Let's just use this red right here. Why is this popping up? It's popping up in a different place. Boom. So change that to red, change that to red, and change that to red to indicate when this one changes, it's going to propagate a change to these nodes. Oh, I guess that didn't go through, right? So now what I could do to detect this change and make sure it gets synced with the server is I could compare the hash of my root node. I didn't actually change the hash, but let's say that this, I'll just change this to G. So this hash changed, this hash would have changed, right? I'll just say X to indicate that it changed. So all those hashes changed, and I compare A, B, C, D, E, F, G with the old hash, which is now different from the server. So I immediately, by just comparing these two hashes, know something in the code base changed. So then there's this process of figuring out, okay, I don't want to copy the whole file system or the whole subdirectory. So let's go figure out what file or files changed. So you'd compare this and then you'd say, okay, server, give me all of the hashes of your child nodes from the root node. You'd compare test, oh, that one didn't change. You'd compare source, oh, that one did change. So I know what changed has to be somewhere down here. Then you would ask the server, give me all your child nodes of source. It would give you back these three hashes. You'd detect this one didn't change. You'd detect this one didn't change. I know this one changed. And then finally you'd go down and make your way to here and realize, okay, scraper is the only one that changed between the file, between the server and the client. So for one, all of this process of essentially doing a search through a tree by comparing a tree on the server to a tree on the client, I didn't have to send whole files. All I had to do was send nodes of a tree, which are hopefully much smaller. These files are, in the example, were actually very small, but obviously real code files might have 1,000 lines in each one. And so now, by just basically exchanging a couple of hashes, I've been able to narrow down, this is the only file that the user made edits to. So this is the one that I'm going to go upload to the server. I'm going to place it in the same spot, and then the server will also update its tree and update its hash so that the root is A, B, C, D, E, F, G. And then maybe this is something that happens, this comparison between the two could be something that's set on a time interval, like every 10 seconds, let's have the client communicate with the server to see if anything has gotten out of sync, right? So then the next synchronization, we would see things are in sync. So there's nothing I need to communicate between client and server. So you can take that example and sort of expand it to any other, other use cases that require synchronizing some large set of files, some large set of data with another server, or it could even be like you have a group of servers that all need to stay in sync together. It doesn't have to just be one server with one client, although you introduce a little bit of complexity there. And this is a great structure, right? We get this advantage of sort of faster searching through tree-like structures. In this case, it's not a binary tree per se, because I've set it up where the directory structure is just mirrored into the tree, but still we can leverage the way that search works and make syncing these two things, one, just go fast because searches through these trees should be fast, and then also not use as much bandwidth and not have to use as much IO because we only copy files that actually change, not the whole directory every time. So that's a quick little overview of Merkle trees. Very cool structure. Go look at the links down below to learn more about how they work.